Hey everyone, myself Bhavya Goyal, a student at IIT Gandhinagar. I welcome you at CodeChef and let's have a look at this question. So yeah, today's question is restricted removals. In this question, we're given two binary arrays A and B of length n and m respectively, where m will always be less than or equal to n. And in one operation, we can choose an index I such that A of I is equal to B of I and I is less than or equal to the min of a comma m, where this represents the current length of a. Okay. And after choosing that element, we can delete a of I from the a, which reduces the length of a by 1, and we re-index the remaining elements starting from 1. So we just basically shift all the elements to the right of the deleted elements to the left by 1. Now, for example, let's say if our a was 10110 and b is 001, we can remove this element because a of 2 is equal to b of 2. We can also remove this element because a of 3 is equal to b of 3. And after removing these two, our new a would be 110, right? And that is the maximum we could do. Like now, none of the a of I is equal to b of I, so we cannot do any more operations, right? We can also have another alternate way of doing these operations and alternate order of doing these operations where we first of all remove this element. So our a would be 1010. We can next again remove this one because these two are equal. So we'll be having 100. And next we can remove this element because a of 2 is equal to b of 2. And ultimately we'll be having this. And again we can remove this element because a of 2 is equal to b of 2. And we'll be having just this left, which is the most optimal way of doing it. So all we need to do in this question is figure out the minimum possible length of A that we can get if we do the operations optimally, right? Now in the input, you can see the input format yourself. We'll discuss the constraints. So in the constraints, we are given that m will always be less than or equal to n, which would be in between 1 and 3 into 10 to the power 5. A and B would be binary. And again, the sum of n over all test cases would not exceed 3 into 10 to the power 5. So yeah, now let's see the sample input to understand it better. So in the first input, we are given A as 0001 and we are given B as 10. The most optimal way of doing it is first of all removing this element and we'll be getting 001 and then removing this element and we'll be getting just 01. And now in 01, none of the element of A of I is equal to B of I. So we cannot get anything better than 01. And the length of this is 2, which is the most optimal we can get. In the second input, we have the array A as 0001 and the array B as just this one. And it is clear that none of the operations can be done. So the answer is straight away 4. That is the minimum length we can get. In the third input, we have 101 and 11. So the optimal way of doing it is first of all removing this element. So we'll be having 01 and then removing this element. So we'll be having just this 0, which cannot at all be removed. So the minimum length which we can get of our array A is going to be 1, which is just this 0. So the answer is 1. Now, yeah, I hope the problem statement is clear. So let's move to the solution. So let's start by observing some patterns and like trying to come up with a brute force solution first. So first of all, if we are removing any element, let's say we remove this because A of I is equal to B of I, would any of the elements before it be impacted? No, right? But the possibility of like the only elements which are going to change in A would be these elements, right? So what if we remove the last element where A of I is equal to B of I every time? So what if let's say we remove this element first, so this got removed. So the possibility of like this was the last element which could be removed, right? And if we remove this element, the possibility of these elements would increase, right? And that is going to be the most optimal one because if we remove this, so and let's say there was a one over here, then this could have been removed earlier, but if we remove this first, then this one would come over here and we won't be able to remove this index. So it's better to remove the last element first and then just shift everything to the left and then check what is the last element now and remove it and then again shift to the left and just keep doing it iteratively. So in n square time, we can get the most optimal way of all the removals, right? Now, how can we optimize this? So let's see this now. So now let's say we are starting to remove the elements, right? So we know that we cannot remove this right now. We know that we cannot remove this. We know that we can remove this element. So okay, we have a counter that okay, we can remove this element as one. Now we know that we can remove this element as well. So we can remove two elements. We can remove this element as well. So we can remove three elements. And we can remove these two elements as well. So we can remove in total five elements, right? Now we know that we cannot remove this element as of now because there is no element below it. But is there a zero where's like some deletions before it would take me? So I can delete at max five elements before this zero, right? And if I can encounter a zero in B in those many operations, I can delete this as well. So what do I mean? So here, let's say like this is five, right? So I can delete this element if in these five elements, like in these five elements, I can get some B, like get some zero. So if all of them were ones, I could not have deleted this because even if I make five deletions, this A of I would never become equal to this B of I, right? But if there was a zero below in any of the last five B of I's, I could have deleted this zero, right? And increase the count by one. And in our case, we can just delete even one element and then I can can delete this, right? And I can and because I can do the operations in any order, I'll make sure that this gets removed, right? Now, similarly, let's say we are trying to check for this. So if I can remove some elements such that the distance between this I and the last one I had is less than or equal to the number of deletions I have made, then I can delete this one as well. Otherwise, I cannot. And this is pretty much the whole solution. So how are we going to implement it? So we'll keep a track of the last one we got in the B and the last zero we got in the array B. So we'll keep keep track of the indices of the last one and last zero in the B. And if the distance between the I, which is the current element in A, and the last one, if A of I is 1, or last zero if A of I is 0, is less than or equal to the number of deletions I can make. That is the number of elements I can delete. Then I can delete the ith element as well. Otherwise, we cannot delete the ith element, right? And this is pretty much the whole solution. We can implement it easily without like any prerequisite, like, right? So let's see the implementation once. And before that, what would our final answer be? So what are we trying to do here? We're trying to maximize deletions, right? So the answer would be like n minus this maximum deletions because we need to print the minimum length of the array. So now let's see the solution in C++ first. So yeah, this is the solution. So we'll start by taking in the input of n and m. We'll be taking an input of our arrays A and B. We'll keep a track of where the last zero was, where the last one was, and the number of elements we have already deleted. Now, if I is less than or equal to m and b of I is equal to 0, that means the last zero was at this ith place. Otherwise, this last one was at this ith place. And if a of I is equal to 0 and I minus last zero is less than or equal to the number of elements I have deleted. That means the distance between my current element and this zero is less than or equal to the number of elements I can delete. So I can bring this element here and delete this element as well. So the count of this deleted would increase by 1. And similarly, if this a of I is equal to 1 and I minus last one is less than or equal to deleted, we can just increase the count. And in the end, we'll simply be printing n minus deleted. Now let's see the solution in Python. So we'll start by taking in the input of the number of test cases. We'll be running a loop for each test case. We'll be taking in the input of n, m, a, and b. We'll be adding this 0 to make it 1 based in text. We'll define our last zero, last one, and the number of elements we can delete so far. Now, if I is less than or equal to m, that means like, and like this p of I is equal to 0, that means the last zero I got in the array B was at position I. Otherwise, the last one I got was at position 1 in the array B. Now, if my current element A of I is equal to 0, and the distance between my I and the last zero I got in B is less than or equal to the elements I can delete. So that means I can delete some elements, bring this I at the same position and delete this I as well. And similarly, if A of I is equal to 1 and I minus last one is less than or equal to deleted, I'll increase the count and I'll in the end we'll just simply print n minus deleted. The time complexity would be O of n because we're just running a